We're going to work to develop three skills related to piecewise functions, the first of which is evaluating piecewise functions, the second being the graphing of piecewise functions, and then we'll finally end with writing equations for piecewise functions. Before we can get to any of those things here first, we're going to take a look at a contextualized example that will help us develop how piecewise functions are used and exactly what piecewise functions are here first. So what we'll see right here is an example that involves the mailing of a first class envelope, and it turns out that it costs $1.35 as long as that envelope does not weigh over 1 ounce, because if it starts to weigh a little bit more than that, there's additional charge, and it happens to be 24 cents per additional ounce of weight on top of that starting fee of $1.35. We're just going to represent this relationship in a table and then also graphically. So let's start putting this into a table. So very simply to start, we know that $1.35 is the cost of mailing an envelope, but that's only if it does not weigh over 1 ounce, not over 1. So it could equal 1, right, or just be under. So let's let W be the weight in ounces, and then we could say that it could be equal to or less than 1 ounce of weight. Now it's not just any number less than W, because we don't want negative weights. That's not going to happen. So it really needs to be above 0, not equal to 0, because if your weight equals 0, you're sending nothing, and that wouldn't really make sense, right? So we should make it a strict inequality right there, where 0 is strictly underneath W, making sure that W actually is a little bit of something at least, right? Okay, so from there, basically the weight can kind of be smushed between 1 and 2 for an additional ounce. Now it's not going to equal 1, because right there it does equal 1. And then right here, it could be equal to 2. Now it's just going to be 24 cents higher than our previous starting price of $1.35. That's going to bring us up to $1.59 there. So if we just kind of continue this pattern, we'll go from 2 until we get to 3. And we add 24 cents, and we've got $1.83, and the pattern goes on, right? So you get the idea. I'll just fill in this one last row right here. If we add 24 cents to that, we end up getting $2.07, and the pattern goes on, right? Okay, so if we represent this in the graph right now, and we let this be the W for the weight in ounces, and then we let this be here the axis for the cost in dollars, what I might do here with this then is maybe label by like 25 cents. So we'll make this, like $1, $1.25, $1.50, $1.75, $2 right there, and then all the way at the top right there would be $3, let's say. Okay. And then in terms of ounces, let's just kind of, I don't know, count by ones every 2 squares. So let's say that that's 1 ounce right there. That's 0 ounces, 2 ounces, 3 ounces, 4 ounces, 5 ounces, and 6 ounces. Okay. All right, so if we wanted to graph kind of this first part right here, we're saying that the cost is going to be $1.35 no matter what, right? So even if it's really close to 0 in weight, it's still going to cost you $1.35. So $1.35 is kind of going to be like right there. So any weight between 0 and 1 is going to cost you $1.35. Now, because of that strict less than, and then that less than or equal to, you're going to have an open dot and then a filled in dot to correspond on that little graph piece right there, right? So then if we jump now to the next little interval right here, when the domain is between 1 and 2, it ends up costing $1.59. So $1.59 is kind of going to be like right here. So you kind of get another little like piece of the function, right? Kind of another little step on the staircase, so to speak. And that's exactly what the graph of this is going to look like. You're just going to kind of have little steps that's growing staircase-wise, because as it weighs more, it's going to start to cost quite a bit more, right? So between 2 to 3, it's going to be $1.83, which is somewhere right there. And then the pattern goes on, right? So this is an example of what a piecewise function is, because ultimately a piecewise function is really just a graph that is in different sorts of pieces, right? And really kind of what's important about a piecewise function is that we recognize that the x-axis really kind of gets divvied up and restricted to certain sorts of intervals, right? So this interval right here was kind of restricting the domain to be just between 0 and 1, and that's where we kind of got this first piece of the function, and the second piece lied in this part of the domain, etc. And so that's really what a piecewise function is. Okay, so I'm not even going to bother to write a definition of a piecewise function. I think if you just look at these pictures right here, you get a really good idea and intuitive understanding of what a piecewise function ultimately is going to look like. So with that, we're really just going to dive into the first of the skills that we want to develop with piecewise functions. And this first skill right here is just evaluating piecewise functions, which means we're just trying to find values of functions, okay? Now, the way this is expressed here, though, is kind of a lot of stuff, right? So this is actually an equation, but it's an equation that says that k of x could equal this, or k of x could equal that, or k of x could equal this, or k of x could equal this, or k of x could equal this. So k of x could equal 5 different things, but not all at the same time. It wouldn't be a function otherwise. So these right here are what we refer to as the domain restrictions, and it tells you like which rule you should use just based on what x value you're using. So it's actually quite simple here, my friends. So we'll just go through all 5 examples, and that will help you see what's happening right here. So the first thing that we want to try to do right here is we want to try to find k of negative 3. So really what you want to look for first is you want to look in these domain restrictions to find where negative 3 is. Which interval does negative 3 satisfy? So of those intervals, it's going to satisfy this one right here because negative 3 is an x number that is less than negative 2. So because it satisfies that interval, what you're actually going to plug into then is you're going to find k of negative 3 by plugging it into that rule right next to x less than or equal to negative 2. So the rule you're using is negative x cubed plus x squared. So doing our work for this then, k of negative 3 is going to be equal to taking negative of x cubed plus x squared. Right, so I put parentheses where those x's are going to go, and then we can plug in our value here of negative 3 that we're plugging in, and then just follow PEMDAS. So we want to make sure that right there that we exponentiate before we do that negative in front. So negative 3 to the third means negative 3 times negative 3 times negative 3. That gives you a result of negative 27, and then we'll put the negative that's still in front of it there. And then when we do negative 3 squared, that means negative 3 times negative 3, which is going to be a positive, ends up being positive 9. So from that, then, negative negative ends up being positive. So we really just get 27 plus 9. So we get an answer then of 36 is the value of k of negative 3 then for that function. Okay. The next example is to find k of 0. So again, you'll want to find which interval of the domain 0 belongs to. So you'll see actually a couple of places where 0 is showing up. But in this case right here, x is not equaling 0, right? X actually has to be less than 0. Versus in this right here, x can equal 0. So you'd want to make sure then if you're plugging in 0 that you're actually going to use that domain restriction right there. So that's the interval of the domain in which you would find 0. So what we're going to plug it into, though, of course, is we're going to plug it into that rule of x minus 2 squared. So k of 0 then is going to be equal to parentheses 0 minus 2 squared, plugging in 0 for x. Following PEMDAS, we'll simplify in the parentheses first and get 0 minus 2, which is negative 2 in parentheses. And then because the negative is in parentheses, right, we're doing negative times negative, which ends up being a positive, and we get an answer right there of 4. For what k of 0 is equal to. Then jumping to the next one right here where we have k of 5. So looking at our domain right here, it looks like 5 is going to fit in right between 3 and 7, right? So the rule we're going to use is 8. So actually for that, if we plugged in 5, right, we're just going to get 8 as an answer because there is no x that we're plugging 5 into, right? So it just like turns out that 8 is always going to be your answer when you're plugging in numbers between like 3 and 7 like you see right there. So that's it for that one. Not too much crazy work that needs to be done to get that answer there of 8, of course. And then the second to last one right here is finding k of negative 3/2 or negative 1.5, I guess, right? So that's going to end up being in this interval right there. Negative 1.5 lands between negative 2 and 0. So you're going to want to use this rule right here of negative 2 times the absolute value of x minus 3 and plug into that then. So k of negative 1.5 then is going to be negative 2 times the absolute value of negative 1.5 minus 3. So following PEMDAS, inside that grouping symbol of the absolute value, you'll want to simplify negative 1.5 minus 3, which is negative 4.5. Now that's still an absolute value, so now you can actually take the absolute value of that number, which is going to end up being 4.5, and then that positive 4.5 can now finally multiply by that negative 2. Negative 2 times 4.5 is going to give you an answer of negative 9 for the function value corresponding to x being negative 3 halves. And then one last one right here is to be able to find k of 10. And you'll see that 10 is showing up right there. 7 is less than x, which is less than 10, but there's no equal to right there, which means that actually 10 is not in that interval of the domain, and actually it's nowhere else in any other interval. So actually for this whole function k, 10 is not in the domain of this function, which means that 10 is not actually a legitimate input into this function, which means if it's not a legitimate input, you're not going to be able to plug it in and get an output, right? So what we can say about k of 10 then is that k of 10 actually does not exist because of the fact that 10 is not in the domain of this function, okay? All right, so now we're going to jump into the second of the skills here, which is being able to graph piecewise functions. So graphing piecewise functions is in a lot of ways similar to evaluating, right? Because when you graph something, you're just creating a table of values to plot points, which of course involves plugging in, right? So what's going to happen here is we have a restriction on our domain where one of the pieces of our graph, the first piece, is going to be when x is less than or equal to 4, and the other restriction on our domain right here is we're going to graph that function only when x is a number greater than 4, okay? Now the actual functions that we're graphing right here are the function f of x equals 2x plus 2, which is just going to be a line because it's mx plus b, and it turns out that the other one right here, f of x equals negative x, also happens to be a line in mx plus b form. So we're really just kind of graphing lines, but we're just going to graph lines that are kind of restricted. So we're not graphing it for all real numbers in the domain. We're just restricting the domain. So how you graph these things should be no different than how you graph lines. So let's start with just the red for right now, graphing f of x equals 2x plus 2. So we know that this number right here corresponds to the y-intercept. So we can start right there. And then this number right here corresponds to the slope, which means that it has to be a rise of 2 for every run of 1 unit. So going up 2 over 1, just like this, right, would be graphing f of x equals 2x plus 2, okay? Now, the thing is, though, that we don't want to graph the entire line going from negative infinity for x to infinity for x. We want to graph the line only when x is a number that is less than or equal to 4. So right here is where x is equal to 4. So this is going to kind of cut off our graph, right? And because we want x to be something that's less than 4, we only want the graph that's going to be on that side of the line. So the only thing that we should have graphed then is just this diagonal line on the left side of that black line, okay? So it'll have an arrow going that way because it will be able to go forever that way. But right there is where it kind of gets stopped at. Where it gets stopped at, you should put a certain type of dot. It's either going to be a filled-in dot or an empty dot, and really that depends on if 4 is in the domain for that piece. And it actually is because of the equal to right there. So you're going to be able to put in a filled-in dot right there to correspond. So I'm just going to kind of erase all of the black stuff that I drew right there because it was really just like scratch work to help us cut off the graph at that particular point. So that graphs the first piece of our function, and then the other piece of our function is to graph f of x equals negative x. So just graph it like you normally would graph a line. So it's going to start at 0, 0, because you can think of it as being negative x plus 0, right? And then it has to have a negative 1 slope, which then means that the graph of your function is going to look like this, okay? But you have to keep in mind, though, that the domain restriction is we only want to graph this when x is greater than 4. So that means then that right on this line, when x is at 4, we really want to only graph the function on this side of 4 when x is greater than 4. So I should only really graph this right here with an arrow to show that it goes on forever in that direction. And that would be just graphing negative x, but only when x is a number greater than 4. So all these other blue dots I can erase. They were just scratch work that were to kind of help me find where to graph that little blue piece. And then I can erase all those black lines there too. The only other thing that I should probably put in the graph right here is that where that blue line got cut off at, I would want to make sure that I put actually an empty circle right there because of the fact that x is not 4 for that piece of the graph. And that's our completed graph. So what you see on the screen right now on just the graph is just like a red little thing and then a blue little thing. And that's really all that you should show in a piecewise function, okay? So that completes that example right there. As we jump to this next example right here, we can kind of speed through this a little bit more since you saw this first example. This is just saying g of x is going to equal -2. So that is just a horizontal line, right, at -2. So it'd just be this line right here. Now, it does say that you want to graph this only between -6 and -1 for x. So what that really means then is that between -6 and -1, right, you're just going to graph that little horizontal line. Because of the equal to's that you have right there, x can be -6 and -1. So for sure, both of those endpoints right there can be filled in dots and need to be filled in dots, okay? The second piece of our graph right here is going to be g of x equals 1 minus x squared. Now, when it's x squared, you know that it's going to be a parabola, right? So if you were graphing just y equals x squared, you know that it's going to be centered at 0, 0. And then 1 squared is 1, 2 squared is 4, 3 squared is 9, and then also -1 squared is 1, -2 squared is 4, -3 squared is 9, etc., right? However, our graph right here, though, has a negative x squared, which means it would flip the parabola upside down, okay? But not only that, but this 1 right here is like added, which means that it also moves the parabola up 1 unit. So really what we're going to see happen then is that the vertex of the parabola is going to be right there, and then it's just going to be upside down. So if we go over 1, 1 squared is 1, right? And then if I go over 2, 2 squared is 4. So I went down 4 units right there from where the vertex is at to get that point. And then if I go over 3 units, 3 squared is 9. So if I count down 9 units, we get down there to a height of -8, which is 9 units lower than where 1 is at, right? Then, of course, that gets copied over onto the other side of the graph, sort of like this. And so that would kind of outline the shape of your parabola overall, right? Now, we do have a domain restriction on this piece of the graph, though, in that only between -1 and 3 do we want the graph of this function. So that really means between right here to right there is only where we want the graph of this parabola. So I really only want to graph the parabola going from here and then stop right where we get there, right? So these extra dots that I have from the parabola can all be erased, and that's really all that we kind of want to have, right? Now, the other thing to think about is the fact that at -1, we're going to want an empty or an open circle happening right there. So I'll draw an open circle there, and then at the 3, we'll have a filled-in circle, kind of like I already have right there. So that graphs that piece. And then finally, the last piece of this function right here is going to be g of x equals 3/4 x minus 5. And that's only when x is, I guess it's a typo on my part right here. So this symbol right here is actually supposed to be flipped the other way. Again, just a typo on my part. So just make sure that instead this right here actually says x is greater than 3, okay? So if we were to graph 3/4 x minus 5, you should know how to graph that because you should be able to start at -5 for the y-axis or y-intercept number, and then go to slope of 3/4, which would be going up 3 and over 4, up 3, over 4, right? So just like that. Now, once you've graphed that, we want to make sure that we actually restrict the domain of this to be only when x is greater than 3. So if we cut off the graph at x equals 3, which is right there, you're going to see that kind of like from here, which is then some sort of decimal number, right? And then onwards, that's where we're going to have the graph. So it's just going to kind of be this line from there and onwards when we have that 3/4 x minus 5. So the rest of this blue line can kind of be erased right there. And that's basically what we'll have. Because it's just strictly greater than 3, we want to also make sure that we put a nice little open dot right there to show that there's not a function value on the little blue line that we have right there. That's it. So that's that example right there. And then the very last graphing example that I'll use that actually has an equation already expressed and written for it is this rule right here. So this first little piece right here is actually a rational function. So if you didn't know how to graph that, you could of course plug this into a graphing calculator or Desmos to be able to graph this. There is some really interesting algebra that happens with this though, because you can see the top part right there is x squared minus 9, which you should recognize as being a difference of squares. When you have a difference of squares, it always factors as the product of a sum and a difference. So you can factor that top part as being x plus 3 times x minus 3. And then the bottom part right there is x plus 3. So it does turn out that when you then divide those things right there, x plus 3 with x plus 3, because they're the same factors, they'll divide to just equal 1. So you really just get 1 times x minus 3 left over, which is really just x minus 3. So actually, like this thing right here really does just equal x minus 3 as long as x is not equal to negative 3. And so x minus 3 is actually just a line, right? Y equals x minus 3. So if you graphed y equals x minus 3, it's really just going to be starting at negative 3 and then going at a slope of 1, like you're seeing right here. So that's going to graph that. Now, the domain restriction on this piece, though, is that x is not equal to negative 3. So basically, every real number is going to be an x value for this line, except at negative 3. So when x is negative 3, then you're actually going to have a function value on the graph right there. So there should actually be like a little hole in the graph right there, a little empty hole that corresponds to the fact that there's actually not a function value showing up in the graph right there. So just to kind of draw that maybe a little bit better, I'll put a hole there first, and then I'll draw the line kind of coming from the hole so you can see that a little bit better. All right, so that takes care of that first little piece, and then the last little piece is pretty simple right here, because only when x is equal to negative 3. So only at negative 3 should we get a y value of 4. So right here, when we have negative 3, we get a y value of 4. So just that little point right there would be that point that you want to graph. And so that blue dot with that red almost line sort of thing is just going to be the graph of that particular piecewise function that we want to have graphed there. All right, these couple examples right here of the floor function and ceiling function, I'm going to skip past here, and we're just going to jump to the very last example here where we are asked to write an equation for the piecewise function that is shown in the graph. So you'll see in this piecewise function, it looks like there's probably 4 different equations we're going to be able to write for kind of the 4 different pieces that we're seeing right here. So I'm going to start with this piece that you see highlighted in the red color right there. So that piece right there is really just a constant function of 6, right? So we should be able to equal 6 on a certain interval of the domain. So after that 6, I'm going to put a comma and then specify the fact that that is really happening from negative 4 and negative infinity between those couple of numbers. So I'm going to be able to say then that when negative infinity is less than x, but then x is less than negative 4, that's when our y value is going to be able to equal 6, of course, right? Notice that both of those are less thans because you can't equal negative infinity, and then also there's that empty dot right there at negative 4, meaning that you're not going to be able to equal negative 4 for an x value there either, okay? And then for the yellow piece that you're seeing right there, that's just a line, so you should be able to write that in mx plus b form, of course. So you can actually see that the b value right there is at negative 1. And then the slope of the line appears to go up 2 over 1, so it has a slope of 2. So 2x minus 1 should be the equation for that line. And then the interval of the domain that that is on is between here to there. So it's really between negative 4 and 0. That has a filled-in dot and has a filled-in dot. So negative 4 less than or equal to x, and then less than or equal to 0 would be the domain upon which that line is restricted to. And then the third piece of this graph, which I'll highlight in blue right there, appears to kind of be like a parabola sort of shape, right? And if you do follow the points from here, it goes up 1, up 4, up 9. So it's, squaring numbers just like a parabola does. So it is like x squared, but it actually starts down at negative 4 is where the vertex would be. So it just means the graph is shifted down by 4. So a subtraction of 4 from positive x squared would be the equation that defines that particular parabola there. The domain that that parabola is on is between here until we get to there. So right between 0 and 3 is where that parabola is squeezed between. So we're going to have, I guess that point right there was actually empty. So it's going to have to be just a 0 less than x. And then right there, we're gonna maybe kind of have to decide because they kind of meet each other. So maybe we'll just say it's strictly less than 3 right there. So then when we kind of do this last part of the graph here in the green, then I guess we'll just have to make the executive decision to include 3 in the domain right there. So 3 is less than or equal to x. And then it goes basically from 3 until you get to 9 right there, which is strictly less than 9 because it has an empty circle right there. So the only thing that we're missing though is to get some sort of equation for that green graph. So it is a line for the green graph. So we're going to want to get the slope and y-intercept. It appears that the slope of the line tends to go from here down to here is another point. So it goes down 1, 2, 3, 4 over 3. So it seems to have a negative 4/3 slope. But we don't know where the y-intercept is, so maybe we'll have to keep going by 3 and up 4. So it appears that right there, actually 9 would be the y-intercept. So adding 9 to a negative slope of 4/3 times with x, that would be the equation for that green little piece right there. So the last thing that you'll need to do is make sure that you close all of these things off using a left brace. We don't ever put a right brace on the other side of everything, just a left brace, and say that this is going to equal like your y value. Or we could also say that when you plug in a particular x value, we do some rule or a function to it. So perhaps the function's name is f, and then we could just say f of x is equal to that.